Okay, so for this video, I'm going to do the math problems on the homework, and then I'm going to do a couple example problems from the math review that I put up. And hopefully this will be helpful to you guys for the quiz. So I'm going to start off with problem 8 on the homework, which says compare the escape velocity from the surface of the Earth for a hydrogen atom with a mass of 3 × 10⁻24 grams, and for the space shuttle with a mass of 10⁻⁷ grams. So this is problem 8, and I'm looking at escape velocity. So big M is the mass of what we are trying to escape from. And in both cases, both the hydrogen atom and the space shuttle are both trying to escape from the Earth. So big M is the mass of the Earth, right? So this symbol is means Earth. That's not how you spell Earth, right? Little m is the mass of what is escaping. So we've got little m for hydrogen is 3 × 10⁻24 grams. Little m for the space shuttle is 10⁷ grams, right? So, and then r is the radius you are escaping from. So both the hydrogen atom and the space shuttle are escaping from the surface of the Earth, so we're going to use the radius of the Earth. Now, looking at this equation, I can see right away that there's no place for me to plug in the mass of what is escaping. So I can see right away that this escape velocity does not depend on the mass of escaping. So they should be the same. And just to double check, I'm going to do V escape velocity for the hydrogen is √2g. For the hydrogen, we've got mass of the Earth and radius of the Earth. For the space shuttle, 2g, again, we've got mass of the Earth, radius of the Earth. These are the same, which is what we expected. They have the same escape velocity because the escape is not dependent on mass of what is escaping. Okay, so that's problem 8. And then problem 10 says if the Earth could be compressed to a small enough radius, it would become a black hole. What is that critical radius? So you think to yourself, okay, what is a black hole? It is something that is so small and dense that not even light can escape. So if light can't escape it, that it tells me that all of its mass has to be small enough that the escape velocity is greater than the speed of light, or is equal to or greater than the speed of light. So looking at this formula for escape velocity, I want to say, so at my critical radius, or so when r is equal to my critical radius, so we'll also call this the Schwarzschild radius. I'm just going to call it RS. Then the escape velocity is equal to the speed of light, right? That's just this definition. At this critical radius, the escape velocity is the speed of light. So I'm going to go ahead and sub in for escape velocity. I'm going to sub in C. And for r, I'm going to sub in this Schwarzschild radius. Now I want to get this Schwarzschild radius, I want to isolate it. I want to get it all by itself on one side of my equation. So to do that first, I'm going to get rid of this square root. So I'm going to square both sides. It's going to give me c squared is equal to 2gm over r Schwarzschild. I'm going to multiply both sides by rs because I want it up on top. It's going to cancel out. I'm going to get rs c squared is 2gm. I want to get rid of this c squared, so I'm going to divide both sides. Those are going to cancel, and I get my Schwarzschild radius is 2gm over c squared. So now I can plug in some numbers for this. So I'm going to do 2. The value of g is 6.67 times 10 to the negative 8. The units are centimeters cubed per gram second squared. And then I've got the mass of the Earth is 6 times 10 to the 27 grams. And if we ask you to do a problem like this on the quiz, then we would give you the value of G and the mass of the Earth and the value of C. So that's 3 times 10 to the 10 centimeters squared, or per second, 3 times 10 to the 10 centimeters per second, right? So I'm just doing this and this. C times C is going to be equal to C squared. So now, since these are in scientific notation, to do this math, I'm going to multiply and divide my coefficients and add and subtract my exponents. So for my coefficients, I have 2 times 6.67 times 6. I'm going to divide that by 3 times 3. Right? And then that's going to be times 10 to the negative 8 plus 27, because that's multiplication, and then minus 10 because those are divided. And I'm looking for a radius. I'm looking for something with length. I've got centimeters in here, so this is going to be centimeters. And that's going to be equal to 8.9 times 10 to the negative 1 centimeters. So that's the same as 0.89 centimeters. But either this or this, they mean the same thing. So there, you can put either one for the correct answer. But what this means is that you would have to take the whole Earth and crush it down to less than a centimeter in radius to get it to turn into a black hole. Okay, so that is the 2 homework problems. And I'm going to do a couple problems from the math review that I put up. Okay, for the problems from the math review I put up, I'm going to start off with problem 1B, which says, what happens to the escape velocity from the surface of a planet if you decrease the mass of the planet to 1/16 of the original mass? So we decrease mass to 1/16 original, but we keep the radius the same. And then what happens to escape velocity? So there's a couple shortcuts that you can take when solving a problem like this. You can do the full way and it's pretty much foolproof. Or you can take some shortcuts and make things a little bit faster for you. So one shortcut that you can take is, we're going to take our formula for escape velocity. 2gm over r. And I'm going to replace this equal sign with a proportional sign And then in here, I'm going to drop out anything that's constant. So anything that doesn't change. So 2 is a number that's not going to change, so I can drop that out. G is a number that's not going to change. I can drop that out. M is changing, so I have to keep that in. R, for this specific problem, is not changing, so I can drop that out. So for this problem, this can get reduced to proportional to the square root of m. And for this problem, you can use either version of this equation to solve it, and you're going to get the same answer. So this can make things a little faster, but if you're not comfortable going from here to here, then that's okay. You can just stick with the full version. So one way to do this without doing out the full math and writing out all your 2 versions of the equation is to just look and say, okay, so, this is equal to this, or this is proportional to this. So anything that happens to this has to happen to this as well. Because, if you multiply something on one side of the equation, you have to do it to the other as well. So if this gets multiplied by 4, this also has to get multiplied by 4. If this gets divided by 2, this also has to get divided by 2. Right? So I can take this root 2gm over r, and I'm going to sub in for m. So my mass is going to go to 1/16. So I'm going to sub in 1/16 my mass over r here. And my goal is to pull out whatever I put in. So I just put in this 1/16, so I want to pull it out. If you have 2 things inside a square root and they're multiplied by each other, then you can put them each in their own square root and have those multiplied. And square root of 1 over square root of 16, same for division, we get 1/4 root 2gm over r. So you can say, okay, well, this is what I started out with. And now I'm going to divide it by 4, or multiply it by 1/4. So I also have to multiply my escape velocity by 1/4. So my escape velocity is going to be 1/4 of the original. If I did this with this shortened version, I would get root m. That's going to go to root 1/16 m. And we get the same thing. I started off with this. I'm going to multiply it by 1/4. So I need to also do 1/4 of my escape velocity. So if that is confusing to you, or get you a little lost, that is fine. We can do it out the long way. So in the same way that we did stuff in the last quiz. So for the last quiz, we did these ratios between star A and star B. But now instead of star A and star B, I'm going to do ratios between my initial state and my final state. So I'm going to say my V escape initial is equal to root 2g initial mass over initial radius. And my V escape final is equal to root 2g final mass over final radius. And now I'm going to look up here for my relations. So I know that my final mass is going to be 1/16 of my initial mass, and my final radius is going to be the same as my initial radius. So I'm going to go ahead and take this here and I'm going to replace this final mass here with 1/16 my original mass. And I'm going to replace my final radius with my initial radius. Looking ahead, I know that my goal is to get something that looks like this, right? Because the total goal of what I'm doing here is I want to get an equation that has both final escape velocity and initial escape velocity in it. Because I want to be able to compare final and initial escape velocity. So when I have this only has finals in it. But I know I want my final answer to have finals and initials in it, so I need to bring in some initials into it, and I do that by doing these substitutions. So now I've got something here that has both finals and initials in it. And that's going to get me on my way to have both final and initial escape velocity. So I know my final goal is to have something like this that I can sub that in for. But just kind of in general, I know that this 1/16 is kind of a stranger in my equation, right? It doesn't really, it's out of place. It's something that I've added in. So I'm going to pull that out to the front. And then I'm going to give it its own square root. And then what do you know? I've got this, which is equal to my initial escape velocity. And that gives me my answer, right? My V escape final is 1/4 V escape initial. And that's the same answer that I got up here when I did this kind of quick and dirty way. But this is, you know, very much written out, tells you exactly their relationship. If I wanted to do this with the shortened version of the equation, I'd say V escape final is proportional to root M final, V escape initial is proportional to root M initial. So my V escape final is proportional to root 1/16 M initial. All right, because I've gone and replaced that with that. I'm going to put this 1/16 in its own one, and then I've got 1/4 V escape initial. So again, I get the same answer that I got before, which is that my V escape final is equal to 1/4 V escape initial. Right? So all these different ways and you get the same answer. So you can do any of the ways as long as you get the right answer out. Okay, now I'm going to do problem 1C, which says what happens if we increase the radius by a factor of 25 but keep mass the same. So in this one, if I want to go down to a condensed version, I want to look at, okay, 2 stays the same, G stays the same, M in this case is going to stay the same, and R is going to change. So we're going to do V escape proportional to 1/R. All right, so that's our condensed version. So if I'm going to do this the quick and dirty way, I'm going to take this 1/R and I'm going to replace r with 25r. And then I'm going to say, okay, well, dividing by 25 is the same as multiplying by 1 over 25. Let's split this up into 2. And I get 1/5 times what I started off with in the first place, which means that I'm going to have 1/5 of my original escape velocity as well. And to prove that, I'm going to say escape velocity initial is equal to 2gm initial over radius initial. Escape velocity final is equal to 2gm final over r final. My mass is staying the same, so my m final is my initial mass. My radius final is 25 times my initial radius. So I'm going to take my v escape final and say I'm going to plug in. For m, I'm going to do initial m, and for radius, I'm going to plug in my 25 times my initial radius, right? So I've just gone and replaced final mass with initial mass and final radius with 25 initial radius. So this 25 is my new thing in this equation. So I'm going to try to pull that away and pull that out to the front. Right? It doesn't belong there. It's not something that we're used to seeing in this equation. So I want to pull it out. Get each of these in their own radical or own square root sign, and I get 1/5. And then this here, this is my initial escape velocity, so I get my final escape velocity as 1/5 of my initial escape velocity. If I wanted to do this with my reduced version, right, they're each proportional to the final and the initial. I'm going to take my v escape final, it's proportional to 1 over 25 r initial. Right, I've just done this substitution. I'm going to pull out this 1 over 25 because dividing by 25 is the same as multiplying by 1 over 25. This here is the same as my initial, so I get 1/5. So again, the same thing. Couple different ways to do it, and I get the same answer no matter which way. Okay, the last one I'm going to do is problem 2, which says the escape velocity from the surface of Jupiter is 60,000 meters per second. So v escape for Jupiter is 60,000 meters per second. If the mass of Jupiter was quadrupled, so mass quadrupled, and the radius shrinks to 1/16 original, what is the new escape velocity? So I'm looking at my formula. If I want to get my condensed version, 2 stays the same, g stays the same, m is changing. R is changing, so I have to leave both of them in there. So I've got V escape proportional to root M over R. Right, so if I'm gonna do this the quick way, got root M over R. That's gonna go to, I'm gonna replace M with 4M, R with 16R. I'm gonna pull out that 4. Dividing by 16 is, oh sorry, this is 1/16. Dividing by 1/16 is the same as multiplying by 16. Four times 16 is 64. I'm going to put that in its own radical. And I get 8 root M over R. This is what I started off with. I'm multiplying it by 8. So I need to also multiply my initial escape velocity for Jupiter, by 8. So if I'm going to do this out the longer way, the escape for Jupiter is 2g mass of Jupiter over radius of Jupiter. So that's our initial state. The escape final is going to be equal to 2g m final over radius final. And we also know that our final mass is 4 times the mass of Jupiter, and our final radius is 1/16 the radius of Jupiter. Right, so I'm going to take my V escape final is equal to 2g. I'm going to replace the final mass with 4 times the mass of Jupiter. And I'm going to replace my final radius with 1/16 the radius of Jupiter. And now I want to get rid of the stuff that I've added in. Right, so I've added in this 4 and I've added in this 1/16, and I want to pull them out. So I'm going to pull out 4. Dividing by 1/16 is the same as multiplying by 16. And this is root 64. I'm going to give it its own radical. And then now I've got this is equal to my escape velocity for Jupiter. So my escape velocity is going to be 8 times the escape velocity for Jupiter. If I do this quicker way with the shortened version, escape velocity for Jupiter is proportional to mass of Jupiter over radius of Jupiter. Final is, for mass of final, I'm going to plug in 4 mass of Jupiter and then 1/16 radius of Jupiter. There, right? I've done that's for that. And then for this radius of Jupiter, I've done the final radius. And then again, I'm going to pull out this 4, pull out this 16, mass of Jupiter over radius of Jupiter. Again, we've got root 64 times root mass of Jupiter over radius of Jupiter. That right there, proportional to my initial escape velocity. So we've got 8. So I've got my proportion that V escape final is equal to 8 times the escape velocity for Jupiter. But I also know from the initial part of the problem that my escape velocity for Jupiter is equal to 60,000 meters per second. So my final answer for this problem, no matter which way I do it, is going to be 420,000 miles per second, or meters per second, is a new escape velocity. Okay, and you always want to make sure that you put your units on your answer and that they make sense. Okay, so that is the homework and some of these math review problems. I hope this is helpful to you, and if you have any questions, please email me, and good luck on your quiz tomorrow.